Electrochemistry, Part 1, Oxidation-Reduction Review. In this video, we will review important redox terms and review how to balance a redox reaction using the half-reaction method. Electrochemistry is the study of the conversion between chemical energy and electrical energy through oxidation-reduction reactions. It has numerous applications, including batteries, industrial production, and electrodes, for things like pH probes and blood and heart monitors. We're going to study two opposite processes: the generation of electricity by a spontaneous chemical reaction and the consumption of electricity to induce a non-spontaneous chemical reaction in the direction that is not thermodynamically favored. To review, oxidation-reduction reactions always involve a transfer of electrons from one reactant to another reactant. Oxidation is the term for what happens to the substance that loses electrons, causing its oxidation number to increase. This is what happens to the iron 2 ion in this example when a chemical change turns it into the iron 3 ion. The oxidation number of the iron goes from +2 to +3. Reduction is the term for what happens to the substance that gains electrons, causing its oxidation number to decrease. This is what happens to the manganese in permanganate when a chemical change turns it into the manganese 2 ion. The oxidation number of manganese goes from +7 down to +2. The mnemonic device that we've used in the past to keep these two easily confused terms straight is Leo goes grr. It's about a lion. Loss of electrons is oxidation. Gain of electrons is reduction. Got it? Leo goes grr. Rawr. Let's review the half-reaction method for balancing redox reactions. Here we have the unbalanced net ionic equation for the reaction between potassium permanganate and iron 2 chloride in acidic solution. I've also got the two relevant half reactions already separated out. We're going to do the same 5 things, if necessary, to each half reaction in order to prepare the two half reactions to be added together. So, here we go. At the top of this slide, I've got the two half reactions separated out: the oxidation half reaction on the left and the reduction half reaction on the right. Let's look at the oxidation half reaction together first. Step 1, I'm going to use the lowest whole number coefficients to balance all the atoms except for hydrogen and oxygen. In this case, there's nothing we'll need to do to balance the iron atoms because there's only one on each side already. Step 2, we're going to add water molecules to whatever side of the equation needs them to balance the oxygen atoms. In this case, there's nothing we'll need to do to balance the oxygen atoms because there are already 0 oxygens on each side. Step 3, we're going to add hydrogen ions, H+, to whichever side of the equation needs them to balance the hydrogen atoms. In this case, there's nothing we'll need to do to balance the hydrogen atoms because there are already 0 hydrogens on each side. Step 4, we're going to add electrons to whichever side of the equation needs them to balance the total charge on each side of the equation. In this case, the left is +2 and the right is +3. So we're going to add 1 electron to the right side of the equation, bringing both sides of the equation to a total of +2 so that it's charge balanced. We can't do step 5 yet until we've done steps 1 through 4 for the reduction half reaction. So let's jump over there to the right side. Over on the right side, we've got the reduction half reaction. Step 1, I'm going to use lowest whole number coefficients to balance all the atoms except for hydrogen and oxygen. In this case, there's nothing we'll need to do to balance the manganese atoms because there's only one on each side already. Step 2, we're going to add water molecules to whichever side of the equation needs them to balance the oxygen atoms. In this case, we'll need to add 4 water molecules to the right side of the equation to give us 4 oxygen atoms on each side. Step 3, we're going to add hydrogen ions, H+, to whichever side of the equation needs them to balance the hydrogen atoms. In this case, we'll need 8 hydrogen ions to add to the left side of the equation to give us a total of 8 hydrogen atoms on each side. Step 4, we're going to add electrons to whichever side of the equation needs them to balance the total charge on each side of the equation. In this case, the left total positive charge is 7 and the right total charge is +2. So we'll need to add 5 electrons to the left side in order to get both sides down to positive 2. Now we can do step 5 for both half reactions. For step 5, we got to use lowest whole number coefficients to get the same number of electrons for each half reaction, so that when we add them together, we'll cancel out all the electrons from both sides of the equation. The oxidation half reaction has only 1 electron, but the reduction half reaction has 5. The least common multiple of 1 and 5 is 5. So we're going to multiply the entire oxidation half reaction by 5. That means we're going to have 5 iron 2s, 5 iron 3s, and 5 electrons. Now we're ready to add the two half reactions together after step 5 to get the balanced half reaction. Adding the two half reactions together, we'll see that 5 electrons cancel out from both sides, as it must if you're balancing a redox reaction. Sometimes you'll have some H+ ions or H2O molecules that cancel out and simplify the equation even more, but not so much in this case. We can double check that our redox reaction is balanced by checking that it is both atom and charge balanced. The total charge on each side of the balanced equation adds up to positive 17. So it's charge balance. There are 5 irons, 8 hydrogens, 1 manganese, and 4 oxygens on each side as well. That means this equation is balanced. Sweet! Now it's your turn. Can you balance the following redox reaction using the half reaction method? Pause the video now so you can balance the reaction. Then continue the video to see my solution. So, spoiler alert. At the bottom of the slide is my balanced redox equation. If you got that equation, then feel free to stop the video now. You're done. If not, or if you couldn't find the pause button fast enough, let's take a look at it together. Copper changing to copper 1 ion is the oxidation half reaction. And once again, permanganate forming manganese 2 ion is the reduction. In step 1, I balanced all the atoms except for hydrogen and oxygen, and as you can see, it was pretty boring. In step 2, I balanced all the oxygens by adding 2 on the right of the reduction half reaction. Nothing needed to be added for the oxidation half reaction. In step 3, I balanced the hydrogens by adding 4 hydrogen ions to the left of the reduction half reaction. Nothing needed to be added for the oxidation. In step 4, I balanced charge by adding 1 electron on the right of the oxidation and 2 electrons on the left for the reduction. In step 5, I doubled all the coefficients for the oxidation, but nothing needed to be done for the reduction. Then I could add the two half reactions together and cancel out the 2 electrons from each half reaction. This final balanced equation is atom balanced and charge balanced, so that's nice. You got any questions? Let me know. In this video, we reviewed oxidation, reduction, and did some redox balancing using the half reaction method. I'll see you next time.